he's a topologist by education, no?
No.
But, okay, that's what he claimed on his webpage, change of mind. He did his study in Moscow, then he moved to probably Передачи информации, correct? Which is kind of Institute for Information Theory in Moscow.
Okay, yeah, wait.
Yes, let me finish.
Fake news.
And then he got habilitation in Germany, moved to France when he got full professor, then the lab, and now he's in Urbana-Champagin, correct?
That's correct.
Good.
Thank you, Wojtek. And yeah, it's much better. Okay. Thank you for Wojtek for the introduction. Thanks to organizer for organizing and inviting me. Holes in the Brownian. Oh, I'm advancing. Okay. Is it the first slide? I don't know. Okay, first slide. Yeah, so let's talk about deals with subject called stochastic topology. Stochastic topology, not the topology in sense of set theoretic ones. It's we're talking about algebraic topology. We're looking at some random sets and trying to understand various topological invariants of them, like something which, like as you all know, keeps their property if you squeeze it or fold it. So we count components, holes, things of this nature. Codified as like homology groups, but and the motivation of it is typically comes from there's two large types of stochastic topology, how you generate those random sets. One of them is you glue them. You take some pieces, a lot of small pieces, and glue them in a random way. Archetypal example is F-Shreni graph. They have a bunch of edges and glue them to some vertices, right? And to study topology, cycles, components, whatnot. So this is one example. It's not what we will be doing. Another large branch of stochastic topology deals with random functions. You have some well-understood topological space, and you have some random functions, and you look at this subset or superset of this random function. This will be something random, and you can study it. And the typical motivation for why we are doing that is coming from material science and medicine. You look at something and ask, okay, so like this is and ask, okay, is this an effect or is just noise? What is the null hypothesis? If you just take a random function, random thing, what it will be looking like, right? So like in this example of perfectly fake fMRI, no people were involved in production of it. And so essentially that's what we will be asking here. And the broad class of those random functions is the Gaussian models, where those functions are sitting in some like functional space, and we pick some Gaussian distribution there, something which we like you take any collection of linear functionals, then the joint distribution of those linear functionals will be Gaussian. So this is the Gaussian element in this functional space, and typically what happens. Okay, so this is what we mean by stochastic topology. Like big, attention to this area was, generated by influential work by Robert Adler and his student Jonathan Taylor, who were studying smooth random functions. And it's not what we will be doing here. What we'll be addressing here is Brownian, so-called Brownian sheets. So like high dimensional generalization of Brownian motions. Definitely something non-smooth. This is like sampled path of a Brownian sheet. You can see it's like all, you take any collection of points, evaluate this function there, the joint distribution will be Gaussian, but it's very non-smooth. So what we can say about that? Okay, so we'll be looking at the subsets or supersets of those functions and asking ourselves, what is the topology of those functions? Okay, so what are those this Brownian sheet. So informally, we can define them as a function which is the integral over a rectangle of a white noise, right? That's how the physicists think about them, and they're correct. This is the right way to think. So you have white noise. Each point here is populated by some, there is a white noise at each point of this plane, and you integrate this white noise over this rectangle. This will be the value at this point x, y, right? So again, this notation, of course, makes no mathematical sense, but it's convenient because you can immediately, derive all, what you're interested in. So yeah, so those Brownian motions, as we all know, exist. Not just exist, they have nice continuous realizations, even Hölder, with a constant, exponent 1/2. And, but, being Hölder, yeah, so, and the sub-level sets, we refer to them as Brownian bubbles, okay? And the Brownian bubbles, so this is an example of several of those subsets of different levels, right? So the whitest is the lowest one that you you can always imagine as you have this very rough looking seabed, and you start to fill this reservoir, and white is where the bottom, then yellow, then red, and the black is uncovered. You can see several things. First of all, those are rough subsets, right? They are have bad boundaries. And indeed, Robert Adler in his early work, before he wisely switched to smooth functions, he studied those Brownian bubbles and proved that the boundaries are pretty fractal, right? They have host of dimensions of d minus half if they're sitting in dimension d. Another effect you can see, obviously, there is some vertical and horizontal structures there, right? And we'll come to that. That's visually obvious, but we'll see why it is the case. Anyway, so the structure of those Brownian bubbles, were covered by many people. Again, like I mentioned, Robert's work, and there was tons of work, especially in dimension 2, by Walsh, Dalang, Monfort, many other people. And but they studied various, asked various questions about the structure of those bubbles, but topology they didn't really study because those sets are fractal. There will be infinitely many, countably many components of them. What do you mean when we talk about topology? The number of components is infinite. The number of holes in those components will be infinite. How to formulate this question properly, it was not clear. So there's tons of pathologies in those Brownian bubbles. Everybody has a collection of their favorite. My favorite is that if you restrict this function to any horizontal line, it has distribution of just the usual Brownian motion, right? The standard Brownian motion, somewhat rescaled. So in Brownian motions, at probability 1, they don't have the points of increase, the points that to the left you're below and above on the right you're above this given level. But if you consider, realization of any of these Brownian sheets, then you do have horizontal lines where you have points of increase, right? So this probability 1 thinks of event of probability 0 happens there. So anyway, so that's bizarre. So how to study topology of that? And natural idea is that you just filter out the noise, you filter out the jitter, you remove all the effects of small size, right? So the small little islands, you just forget about them. But it's hard, when they're small, it's very hard to do that. There's no natural way to filter them by size. So in this talk, I will be deploying a different way of filtering. I will filter out those small debris, small islands, and small holes. I will filter them using a different tool, not by their horizontal size. So this different tool has a name. It's called persistent homology. And you may have heard about it. It's a tool. People use it in so-called topological data analysis. and where, with the same motivation to get rid of various noise. And okay, like a little bit of technicalities here. So like what happens, again, like remember, we have this rough C bet and we start to fill it up. And at each level, we're asking, okay, what's the topology of, of this field space? And so in this field space grows with the time, right? As we fill it more, it gets bigger and bigger. So like when you compute homologies, what you do, you take so-called cycles, things without boundary, and remove those which are bounding something. So like remove something which is, like non-interesting, like keep cycles, so keep different components. So this is like, there's an algebra there, and this is the typical definition of homology group, is you take the cycles and divide by the boundaries. And in our case, both cycles and the boundaries, it's wild spaces. Again, like countably many components, very unpleasant. So this is my artist rendering of this picture. So this is the usual. So this is like your this is your cycles, and this is your boundaries. You factor one by the other, and you have this a lot of jitter. Like a lot of like these tail ends, a lot of jitter. So the persistent homology tells you a different story. It tells you, okay, as in the previous picture, I'm sorry. Yeah, it tells you take the cycles coming from level S, but factor by the boundaries coming from higher level. So you remove all this jitter in this picture. You're left with something smaller, compact. So what it looks in the reality is shown here. So this is examples of several. So again, there are two level sets, right? The purple is the lower level sets. The bluish one is the higher level set, right? So those two guys, they are present at the blue level, but they were not at the purple level. They're not persistent. They're not there. This guy was present at the purple level and survived, like still there, like in the blue level, obviously. So this is persistent component. This component is there. Here, two components at the purple level, but when you fill it up, they're actually just one component. So you say, oh, here we have one persistent component. One of them was there, but it merged with the better one, the surviving one. Right? So there is a rule how you select which one survives, but we come to this later. So here, it seems that you have a cycle, you have a hole in the middle. But this hole is not persistent because at the lower level, it was not there, right? So the hole was formed when we filled up this, right? So it's not a persistent hole. But this hole is persistent, right? It was at the lower level and survives at the higher level. This hole was at the lower level, but is not at the higher level. It's not persistent hole, okay? So we have one persistent hole, 1, 2, 3 persistent components, okay? So this is how persistent homology works. This is how we filter. We look at the patterns which emerge at some level and survive at some higher level, okay? So. Still, at each level you have this, like infinitely many of those components, countably many. Will this filtering work? Well, like there is a sort of in this theory of persistent homology, they call this filtration, they call this filling up pattern as tame if for any pair of levels S and T, the number of those persistent, like the ranks of those persistent homologies is finite, right? So like if you have a good prospect of analyzing it really, then it's called tame. And if you have something tame, then you can describe it in, like in a reasonable way. So the way to describe it is, okay, so this is like important diagram, so let's concentrate on it, spend some time on it. Again, apologies to those who already saw it many times. So here we start to fill it up. So here the first component appears, right? Then another component appears, the third component appears, fourth component appears. So like now we have this 1, 2, 3 components growing, but then at this point, this component will merge with that one. there is we call it an elder rule, which says that whoever started early survives. So this guy started early, survives. So this guy dies, right? So it's a little bit like this Department of Government officials. They kill the youngest one first. So yeah, so we have the situation. So like whoever can spill into deeper end survives. And yeah, so this have and like the one component, of course, survives throughout. You know, if there's like one connected component. So how we depict this data? So like this little component which was born here and survived there, we depict it as a dot, right? We just take the two-dimensional dimension 2. We say, okay, the birth date and the death date, right? And we depict it as a point. So for each of such filtrations, each such function, we associate such a measure, just a point process, such a collection of sum of delta measures, which tell you where somebody appears and when somebody died. Okay, so this is called persistent diagrams, and that's what we'll be studying. The tameness of persistent diagrams, in other words, means that for if you pick any quadrant, any point here in the upper half plane, then and take this northwest quadrant, the content of this northwest quadrant will be finite. This is the tameness. Okay, so and you know, like luckily for us, continuous function of compact spaces are tame, or compact fine dimensional spaces are tame. Okay. So important question is stability. Stability says that you know you have a function and perturb it a little bit and see not small, you know, like supreme norm perturbation. Then you get a new diagram. You need persistent diagram. So this gives you blue persistent diagrams. This gives you red persistent diagram. And those persistent diagrams are close to each other. This is the essence of stability. The closeness understood as the following way. So you take any rectangle and take slightly larger rectangle, then you know under the perturbation, content of the larger rectangle is not growing much. Is not less, is not dropping. You know, the content of the larger rectangle is not smaller than content of the smaller rectangle. Yes, Robin.
Persistence is always with respect to a fixed period of time, so that's the bottom.
Okay, so if you want to understand what survived, what was born before S and survived after T, we take this point S and T and look whichever sits in this quadrant. Right? So this is our filtration. We say, okay, we look at what was born before and survived after. In other words, we look always at this you know, particular persistent diagram, so look content of this particular quadrant. Say it again.
The diagram handles all pairs of times that are between the bottom
or they handle everything, right? It records everything, right? So if I'm interested in what was happening, was born after this time and before that time, I will capture those 2 points, right? I will capture, you know, like I will capture this guy and that guy, and these 2 guys will remain outside of my purview. Okay. So anyway, stability is important property. Again, people write a lot about it just for the sake of writing about it, but you know, like it is important material for our presentation. Okay. Now, so far so good. Now let's look what happens in dimension 1. So what happens if we just our topological space is just one dimensional and we have a function on it, and this function will be just a Brownian motion, right? So we have a Brownian. Oh yeah, sorry. Before we go to one-dimensional situation, so in this talk I will be dealing primarily with the Brownian sheets with the drift, meaning I will be just you know, I will be looking at this white noise which will be slightly displaced by some positive constant. Why? Because the formulas are nicer. The techniques will work in other situations, but you know, like you will see why in a second. The formulas will get compact and inoffensive. So, like, let's look at start with the dimension 1. We have just one dimensional, just a usual Brownian motion with drift. and see what happens. And yeah, there will always, there will be no sigma because by the scaling of space and time, I can always assume that my volatility is equal to 1. Okay, so one-dimensional situation. So you have this, this is the some like fictional realization, this Brownian motion. And it's clear why, what I'm looking at various wells, like spanning some particular, so I take some S and T, so this is my level set, and I'm looking at what spans particular, levels S and T. And it's clear that in this situation, the number, wherever I choose, the number will be constant. If I just consider the usual Brownian motion without the drift, I will have to cut off it somewhere, right? So to keep the number of those, dots, to make the space compact, we will have to restrict my domain. Here I can keep my domain the whole, positive real line because, the number, like eventually you just go away from any interval in S and T, so everything will be compact by, automatically. So that's the main reason why I'm keeping to the Brownian motion with drift. Okay, so Stormy Brownian motion, what we can say about this persistent homology in this case? Again, like essentially, like we are looking at the components which were, started before this level. Say this component started before this level, but only one of them survived. So this will be just one-dimensional, just one contributing one dot to this persistence between levels S and T. And if you look at this picture for a second, you recognize it. Or any one of you who ever taught the introductory course in stochastic processes recognize it as the picture you see in the proof and Dup's proof of the martingale convergence theorem, right? This is the up crossings, right? So you wait until you reach the level T, then you wait until you reach the lower level, and so on and so forth. And inspection this picture tells you that the number of those components which started before T and started before S and survived up to T is just equal to the number of those upcrossings. So there is one component, second component, and third component, right? So number of upcrossings is 3. Okay? So means if you have like Markov trajectories, say Brownian motion with the drift, then you know everything. And indeed, immediately, by strong quantum property, the number of dots, if you have this, Brownian, path with the drift, the number of those upcrossings, the content of our quadrant will be just the geometrically distributed random variable with, this parameter. And from that, you can immediately deduce the density of this point process. Again, remember, function is random, means these dots is random point process. And to characterize the point process, you start with understanding its density. What's the probability that there is a dot in some particular small square? And the density is given like very explicitly by this formula. Again, the Markovian property depends only on the length of the interval you span. So what is interesting here is that and again, remember, just because the Brownian motion is very fractal, so you have infinitely many components sort of at any given level, it's clear that the density should explode towards the diagonal, right? It is same, so if you take any quadrant strictly inside, closed quadrant strictly inside the upper half plane, then you will have the finite content, but like the density should go up if you approach diagonal, and this it grows like delta, this distance to the diagonal to the power -3, and this -3 actually has a significance. So there is a theorem which by me and Schmoll, Weinberger, which says that if you have an alpha Holder function on d-dimensional space, then this function is locally like integrable. So this is your density, and this is Holder exponent and d. And moreover, for generic function, so the functions up to like outside of the meager, like in the Bohr sense, generic function, like typical function, will have exactly this, growth. And in our case, the Brownian motion has, like this Hölder with parameter, half in one dimension 1 divided by half is 2. So like this, delta to the minus 2 times, delta squared times this should be, like barely integrable. That's exactly what you would expect. So anyway, delta to the minus 3 is what you would expect. It's what you get, which is nice. Anyway, so dimension 1 is easy. And again, like the fact that I'm concentrating on the Brownian motion with the drift is just the artifact of the having formulas. Nice, but like in general, you can derive similar results for any Brownian motion. Yeah, this is my point process. Yeah, 0 means I'm concentrating on 0-dimensional homology, just the components. And there is no other homologies on the line, right? On the line, you cannot have 1-dimensional homology. Oh, sorry. Yeah. So for each x and y, content of this square is a random number, right? Which is distributed as a geometric random variable. Right? From that, we can immediately derive density by taking expectations and taking partial derivatives. Okay? Okay. Now back to high dimension situations. So high dimension situation, as I mentioned, sort of more complicated, but not that much complicated, not that much more complicated. So first of all, of course, we will be doing some asymptotic story. We'll be doing some rescalings. So what rescalings we'll be doing? So remember, we started like my Brownian, like high dimension, high parametric Brownian motion is defined by this, the content of this white noise and this rectangle. So if I pick a base point T here and shift it a little bit, so I take point C, which is far out there, and I'm looking what happens, when I restrict my, my function to this yellow, this yellow region. So what is the value here compared to the value there, right? So what is this? But clearly it will be integral over this strip, integral over the blue one, and integral over the yellow one. And of course, T is somewhere out there, so we have to rescale something, right? So rather than consider this psi variable, we consider some different variable, and we consider the variable in such way, so we introduce new variables, which will be, like here, it's a vector, it's psi1, psi2. So we introduce new parameters. This S1 will be just the area of this blue one, right? The area of blue one depends only, okay, it should be S1, S2, but sorry. So the area depends only on this width, right? Again, this point is fixed, so the area of this blue one depends only on this vertical coordinate. The area of the red one depends on the horizontal coordinate. So if you do this, like necessary computation in high dimensions, then, like this is the right rescaling. So this is in formulas what I said in words. And then, like your function can be written as the sum of, like remember this will be blue, there was yellow, there was red. In high dimensions, you will have this like big slabs of stuff. Right? In high dimensions, we have something like right. So there will be like this will be this slab, right? Essentially very large and thin on 1 dimensions, and there will be slab which will be thin in 2 dimensions and so on. So this will decomposition. And if you look at this decomposition, only the slabs which are thin in, in just in 1 dimensions will be contributing. In those slabs, so if you consider, again, if you consider this slab, so content, the area of this guy depends only on y. So it's essentially it's just one function of one variable. The area of this slab, let's call it eta, this will be depending only on this, on psi. So the sum of the areas of this and that slab will be sum of two functions. It will be not function of two variables, it will be sum of two functions of one variable. And of course, this little rectangle here. And if you do all this necessary computation, you will see that all the small rectangles, they scale. Like if you take anything with like where more than one dimension is thin, they will be scaling. They will be like they will be small, and it gives you results. So essentially, your function will be close in S naught norm for T is large enough with high probability to sum of one-dimensional Brownian motions with drift. So of course it simplifies matter dramatically, and of course the people knew for a while, at least for like 45 years, that this multi-dimensional, multiparametric Brownian motion is, essentially indistinguishable from the sum of functions in, sum of univariate functions. And indeed, like this, when you do this integral, it's the same as to say that this, the second partial derivative of your Brownian motion is whatever this white noise. So essentially what you're doing, you're having this wave PDE. So this, of course, is a wave PDE, this like two-dimensional wave equation. If you turn it a little by 45 degrees, you will see it's x squared minus y squared. Sorry, the second derivative with respect to x is minus second derivative with respect to y. So like, yeah, singularities propagate along the characteristic lines, which will be just, parallel, the lines, the directions parallel to the axis. And that's what we see here, right? So you see the propagation of stuff along the horizontal vertical lines. Of course, the same effect persists in higher dimensions. It just is like the usual PDE story. So anyway, so we have this nice connection. So essentially we say, okay, we have this high dimensional Brownian motion, and we can, represent it up to a small correction. We can represent it as the sum of one-dimensional Brownian motions. And here the stability kicks in. It tells us that essentially the persistent diagrams for the multi-dimensional Brownian motion will be reduced to persistent diagrams of the sum of those one-dimensional Brownian motions. Okay, so we can formalize the theorem. So again, you restrict everything to some compact sets and so on and so forth. So, but any compact set, you will have this convergence of persistent diagrams of the original Brownian motion with drift to the sum of univariate Brownian motion with drift, to additive Brownian multidimensional Brownian motions. Okay, but how we can compute? So now we know that it's not a function of d variables, it's the sum of d functions of one variable. How we can compute the persistent homology for the sum of d functions of one variable? What we can do here? But before we answer that question, I want to do a little bit of an interlude to talk about the, what is. So far, the talk is a little bit outside of the normal topics of this audience. So I want to talk a little bit, spend some time talking about trees. Okay. So persistent homology. Remember, when I was talking about persistent homology, I was saying it's just component, right? Zero-dimensional homologies are just components. You're looking like which component, they're born somewhere, and then they merge. And I was say that the youngest will be killed. So we'll say, okay, this is the youngest will die first, the oldest will survive. But there is more information. You can just actually remember, oh, this component merged with that component. So you can form the so-called merge tree, right? So again, before the picture didn't contain this, it was saying, okay, so this, this component was this component. But we can say, oh, this component is actually, this component is merging with this one. So we have, when we just look at the components, not like high dimension effect, high dimensional holes, just components, we can gather more information. We can gather the thing which is called merge tree, right? Just recording how those components glued where they were born and how they get together, right? So again, before we skip the red step, now we're including the red step, and how you go from the red step to the green step, how you go from merge tree to persistent diagram. So here's an iterative algorithm. You take the deepest leaf, take the deepest leaf, take the corresponding stem, and remove the stem. Then you will be left with some subtrees, and you iterate. So it's iterative procedure. You take this like longest stem, remove it. You have a forest, and for each tree of this forest, you keep removing the longest one. And the result, when you get just a pile of branches, before burn them, you just like this is your persistent diagram. Okay. So when you want to reverse, if you started this persistent diagram, if you want to reconstruct the tree, you have to remember, okay, this guy was attached to that guy. So there is also partial order here. So this guy should be attached to that guy. So you have to remember information to this one, because this guy could have been attached to that guy, right? Anyway, so there is this like merge trees. It's a fine object. It's a more precise characterization of like how our filtration works in our topological space. And now we're in the situation, okay, so like the formal definition of the tree, of merge tree on any space. And of course, we all know this construction. If you have merge tree as a planar tree, then as a plane tree, then you can like reconstruct your one-dimensional function by usual contour walk. Okay, but now we are okay. So a little bit more nonsense. So if you have this more merge tree, remember merge tree is coming from so we have this function. And we have this merge tree. We have this merge tree like this. And so you can think about merge tree as a topological space itself, right? It's a path metric space, right? You have 10 points. You can say, oh, there is a path connecting them, the length of this path. So it's topological space. So it's topological space by itself. It's metric space. And it's a metric tree. And there is a function in this tree, right? Because each of these guys is coming from a particular level. So there is intrinsic. So if you have function f, you can produce the tree, the merge tree of f. But then you have the function, corresponding function. So you have a new space and a new function of them. So what will happen if you form the merge tree of this new function? Of course, you'll get the same tree. So merge tree of the merge tree is itself. It's like, again, I'm sorry about talking about banalities, like it's a category theory conference. Okay. But, okay, now more interesting stuff. So what happens if you have two spaces, x and y, and you take the product of those two spaces, and again, it's like very close, we're getting closer to where we were before, right? We have one space, another space, and we have a function of one and the other, and we can form the sum of those functions just by, the function of one variable plus function of the other variable. So what will be the merge tree of this new function? Turns out that the merge tree of the new function depends only on the merge trees of the old functions. So it means this operation is defined at the tree level. You have a tree, another tree, you can form the product of those two trees, and you can form a new merge tree for the sum of those two functions. Oh no. Oh no. Okay. So it means we can turn merge tree into something which we can add them. So now we can add merge trees. This addition is continuous in Gromhauser space, and this is an example, right? So you have one merge tree, so it will be a function of this variable, another merge tree function of this variable, then again function of two variables, and again form, like say how these guys are merging. So first these two guys merge and so on. So the sum of those two trees will be another tree. You can study them. So there is a, there's a monoid, there is a unity there. The unity corresponds to the class of the function x squared. Like you have one leaf starting at 0, goes up to infinity, and so on and so forth. Anyway, So you can ask tons of various questions about those about this monoid, what are central limit theorems, and so on. You know, anyway, a lot of stuff to think about. Back to our Brownian situation. So now we have this situation. We have this. We have the function. So remember where we were. Okay, maybe just the slides will show itself. Yeah. Yes. Okay. So we have a function which is essentially, essentially the function, the additive Brownian motion, the function of this variable plus the function of that variable. What we can say about the components and the holes in the level set of this function. And luckily enough, there is a theorem. There is, again, like in topology, when you take the product of two spaces, there is a way to compute homologies with the product of two spaces. It's called unit formula. Here we have also product of spaces plus some functions. Functions on one space and function on another space give you a function on the product of spaces. It turns out you can just compute all these pieces of our puzzle by looking at this formula where these perps and tops tell you something. So what they tell you? So this is the picture. Okay. So assume you have bar. So like it's born here and dying there, and another bar born here and dying there. So those two bars will produce two new bars. These two new bars, okay, what is going on here? No, yeah, okay. So these two new bars will be those two. So how you compute them? You just draw this rectangle and do the usual convolution projection. So the bottom will be where this guy sits, the top will be where this guy sits, and the length of those two bars will be the smaller of those two lengths. So you have small, like this short length, short bar and long bar, and the two new guys produced will be those two guys. They will be sitting in different dimensions though. If this bar was in dimension k, this bar was in dimension L, then this bar will be in dimension k plus L, and this bar will be in dimension k plus L plus 1. Anyway, this is sort of a little bit piece of combinatorial information, which is important to compute stuff. And it resolves all our troubles because we know what happens you know what happens in all our dimensions. Okay. Yeah. So here's like ugly formula. So if you have a density, okay, this was, so you have a density, one density in dimension k and one density in dimension L. Sorry. Yeah, if you want, you can define this two convolutions. One convolution is coming from the sort of bottom one, right? The perp one. Another convolution coming from this addition of the top ones, right? And this formula does nothing but encodes this picture on the previous slides. It tells you how to compute the densities for those bars if you know the densities for each components of the product. Anyway, it's just to prove that there are formulas. It's not just pictures, right? And then the density for, oh no, what is going on here? Sorry about this. Okay. Okay, it's not working. So anyway, so there is so the density, so what will happen is that, okay, sorry about this. Yeah, so those two convolutions, I don't know what is going on here. Let me try to reduce the size once again. Worked on my computer. Don't know why it's not working here. Yeah, so essentially it tells you that how to compute everything. And so in our situation, it's sort of So what's happening? So we have two Brownian motions, one and the other, and each will produce just the zero-dimension persistent diagrams. So each produce will pictures like that. Like the dots will be accumulating towards the diagonal. That's not really the point here. And then what we can do is we can say, okay, so each dot, one dot here and one dot there, so those are all zero-dimensional one. But they will produce, the pair of those dots will produce two new dots, one in zero-dimension diagram. So this is F, this is Brownian motion 1, this is Brownian motion 2, and this is Brownian motion 1 plus 2. This Brownian motion, the additive Brownian motion in the space of twice the side will produce now two diagrams. One in dimension 1, this persistent homology in dimension 1, persistent homology in dimension 0. So again, those 2 points will produce one dot here and one dot there, which is reasonable. Which is reasonable because on the plane now you can expect to have holes, right? Now you can have dimension 1. Right? Sorry. X enters through delta. Delta is y minus x. Yeah, so here we're integrating with this x and this with y. This. Okay, say it again. Because this is a function of delta. Yeah, we can write an integral with respect to y. Fix x integral with respect to y. We just introduce a new variable delta and.
No, I'm just asking why it is not symmetrical.
Oh, yeah, this should be delta, of course. Yeah, sorry about this. This is delta. Yeah, copy pasting never works. You always miss something. Yeah, should be delta. Thank you. No, it should be x prime plus, yeah, so it should be analog of whatever. Yeah, mistakes. Should be x prime plus delta. Should be x prime plus delta here. Yeah, so this should be x prime plus delta, I guess. Anyway, so what happens here, you can take those two densities, and now you're generating densities in dimension 0 and 1. If you have the Brownian motion and the additive Brownian motion in 3 variables, then you'll be producing something in dimension 0, 1, and 2, and so on. So in dimension-wise, it is working because we start with something which has only persistence in dimension 0, and you're generating various pictures in higher and higher dimensions. Okay, sorry about this formula. So and you compute stuff, right? So this is the formula for the density for the persistent for zero-dimensional persistent homology density dimension 1, and again it's some formula, whichever it means. You don't want to look too attentively. What's important again is that here it blows up towards diagonal to the power of 5. And what is 5? 5 is d, which is 2 in this case. Dimension is 2 divided by half, so it's 4 plus 1. So before we had 3, which was 1 divided by half plus 1. Now we have 2 divided by half plus 1. Everything is as it should be. Okay. So the summary. First of all, I hope I convinced that the filtering topological features of the Brownian, high-dimensional Brownian motions by persistence rather by size. And again, there's tons of, not tons, there's some very interesting work with the people essentially looking at the how these Brownian bubbles or additive Brownian bubbles behave when you filter them by size. For example, Geber-Pitt's work on square root of 17 is can be rendered in this in those terms. However, it seems that persistence gives you much more natural answers and much cleaner formulas. Yeah, so additivity is the key tool, and again, stability persistent diagrams turns out to be very important. And my last, yeah, And my last thing is that this, so we have this new additive structure on the merged trees, which definitely deserves to be investigated, especially by this community. Okay, with this I will stop.